Hi folks, I'm Mr. Fullerton, and today I'd like to talk to you about conduction and induction. We'll describe the differences between conductors and insulators. We'll explain the difference between conduction and induction. We'll talk about how an electroscope works. And finally, we want to recognize that objects that are charged exert forces, both attractive and repulsive. So let's dive in. Conductors are materials that allow charges to move freely. These are typically things like metals that have a bunch of free charge carriers. Usually these are electrons. So metals are good conductors because they have a lot of free electrons to carry charge. On the other hand, you have insulators. They don't allow charges to move freely. They usually have very few free charges. Things like glass, plastic, and rubber are very good insulators. Now, we describe how good a conductor or insulator is by talking about its conductivity or its resistivity. Conductors have high conductivity and insulators have very low conductivity. The inverse of conductivity is called resistivity. Insulators have very high resistivity, while conductors have very low resistivity. The symbol for resistivity is the Greek letter rho. The symbol for conductivity is the Greek letter sigma. So resistivity is 1 divided by the conductivity. Or you could also write that conductivity is 1 divided by the resistivity. Now when you hear about semiconductors, these are materials that when they're pure are pretty good insulators, but by adding certain materials to them known as dopants, you can make them much better conductors. Now, let's talk about charging by conduction. Materials may be charged by contact, which we call conduction. That means the charge is transferring from one object to another. The charge never goes away or is completely created because the law of conservation of charge says that charge is never created or destroyed. It's just sort of moved. So, if you take a balloon and you rub it against your hair, some of the electrons from the atoms in your hair are transferred to the balloon. Then you can go stick a balloon to the wall. The balloon has extra electrons. Your hair has a couple fewer electrons. The amount of electrons that you added to the balloon is exactly equal to the amount of electrons that you lost from your hair. So your hair has a net positive charge. That balloon has a net negative charge. Now when we think about charging by contact, key is remembering that the charge must come from somewhere. And usually, well, almost always, that charge is going to be carried by electrons. So if an object gains electrons, it becomes negative. If it loses electrons and was neutral, had a net charge of 0, if it loses that negative charge, its new net charge is now positive. Let's take a look at a sample problem. If a conductor carrying a net charge of 8 elementary charges is brought into contact with an identical conductor with no net charge, what will be the charge on each conductor after they're separated? Well, if you have 8 charges on one, 0 on the other, you bring them in contact. Remember, in metals, charges are free to flow, so they'll want to distribute across the two. They'll share. That means you will start off with 8 in one, 0 in the other. When they touch each other, they'll share. They'll each have 4 elementary charges. Then when you separate them again, they'll each have 4 elementary charges. So 4 elementary charges on each when you're all done. Another sample problem. Say metal sphere A has a charge of -2 units, and identical metal sphere B has a charge of -4 units. When they're brought in contact with each other, they're going to share and have a total of -6, so that when you split them apart, now A has -3 and B has -3. So the final charge on sphere B will be -3 units. Let's take a look at one more sample problem here. Compared to insulators, metals are better conductors of electricity because metals contain more free metals have more free charge carriers. That makes them a good conductor, and almost always the charge carrier is going to be electrons. So here we're talking about more free electrons in the metal. One tool that we can use to detect electrical charges is known as an electroscope. It looks kind of like you see here on the right. You have a beaker of some sort. Inside it is a conducting metal rod, and that rod is connected to 2 very thin conducting leads. so that if you touch a charge to the top, what happens is that charge distributes through the conductor. The two leaves each see the same charge, and remember that like charges repel, so the leaves spread apart. Let's see if we can't demonstrate that here. I have a charged rod. I'll try and bring it into contact with the electroscope. If you can see the leaves there, as I bring it closer, you can see the leaves start to pull apart. The closer I bring it, I put charge on there, the leaves spread apart. The operation of the electroscope. Now, conductors can also be charged without coming into contact with another charged object. That process is known as charging by induction. If we take the example of the electroscope again, let's say that we start off with a neutral electroscope, has the same amount of positive and negative charges here, but we bring a positive rod close to it. When we do that, because opposite charges attract, the electrons that are in the rod all come up near the rod. They want to be closer to it. That leaves a net positive charge toward the bottom in the leaves of the electroscope, so you'll see it diverge a little bit. Now, instead of touching that charge to the electroscope, what happens if you connect that rod to ground? Where when you connect something to ground, you're connecting it really to the earth, which is like an infinite source of electrons or an infinite drain for electrons. Whatever charge you need, the earth can provide. It's so big, it has tons of charges that you can use. Well, now because you see all this positive charge right near the knob of that rod, you're going to bring in all these negative charges from the ground, because the positive charges attract the negative charges. They'll all accumulate here. Then when you disconnect that ground and leave everything as it was, you end up with that net negative charge on the electroscope. So the whole entire thing became charged, but you never actually touched your charged rod to the electroscope. It just came close to it, and then you connected that to ground. That's known as charging by induction. So, to induce charge in a neutral object, you can bring a strong positive or negative charge close to that neutral object. The electrons in the neutral object tend to move toward a strong positive charge or away from a strong negative charge, leaving the other end of that object with the opposite charge. The object itself, though, remains neutral as a whole. The electrons never go away, they're just moved. Portions of the object are more positive and portions are more negative, however. A positively charged object can be attracted to both negative and neutral objects this way. For example, if you were looking at putting a balloon near the wall, if you charge up a balloon and put it near the wall, the atoms, the molecules in the wall, are actually polar. The electrons spinning around them will spend a little bit more time either toward a positive charge or away from a negative charge. So in effect, you get a local charging of a neutral object. So you'll have a little bit stronger force of attraction than you'll have of repulsion, and an object will stick there. So a positive charge can attract a negative charge or a neutral object. A negative charge can attract a positive object or a neutral object, which means really the only way to ever prove something is charged is by repulsion, because neutral object can be attracted by charged objects, positive or negative, but you can only repel if an object is charged. Sample problem number 4. A positively charged glass rod attracts object X. The net charge of object X may be 0 or negative, 0 or positive, must be negative, must be positive. Well, if we have a positively charged glass rod, remember a positive charge can attract a negative charge, or it can attract a neutral object. So the net charge of object X, which is attracted to that positively charged glass rod, can be either 0 or negative. One last sample problem here. Which diagram represents the charge distribution on 3 neutral metal spheres when a positively charged rod is brought near sphere X but does not touch it? Well, since we have metal spheres and they're touching, the charge can move back and forth between them. So if we have a positive charge here on the left in all of these diagrams, that means that the negative charges, the free electrons in those metal spheres, are going to want to go near that positive charge. That will give us number 4, leaving a net positive charge furthest away from those spheres. So we've set up a local area of charging, even though the net charge on those metal spheres is still neutral. Hope this was helpful. If you need more information, check out aplusphysics.com. Thanks for your time and make it a great day.